Hi, my name is Clancy. Today we're going to be doing 3 and 4 point bending using an aluminium beam. Okay, so this test or this setup you should be familiar with from EGB 121, but today we're going to be doing some slightly different tests. Okay, so in your pre-labs, which you should have completed or you will complete after watching this, we want you to generate your deflection equations for the 3 point and 4 point bend setups. Okay, so you want to be using, or you can use your Macaulay equations to do that, and I would recommend using those. And you'll also need to identify where your maximum deflection is located, and you'll also need to construct an equation for that as well. Okay, so in terms of the prac today, like I said, we'll be doing some 3 and 4 point bending. We'll be using an aluminium beam, and the dimensions of the aluminium beam we have calculated using some calipers. Okay, so we found that the width through here is 19 millimeters, and the thickness here is 3.1 millimeters. Okay, so it's made from aluminium, which means it has a Young's modulus of roughly 69 gigapascals. Okay, so in terms of the important components when we're doing the test today, okay, so we have these two dials on the end here, which we will use to set the length of the beam. Okay, so if we apply a load there, these are essentially our supports on either side so that we end up with a simply supported setup. Okay, we then have the dial gauge on here, which we'll be using to actually measure the deflection. So you can see there when we apply a load, this tip here moves up and down, and it will allow us to measure the deflection at that given point. Okay, and then the other important thing is this little clip that we can load onto our beam, which allows us to apply the loads on here. Okay, so that's important. We need to make sure that these are all positioned in the correct places so that we can get the measurements that we're after. Okay, so the first test that we'll be doing is a 3 point bend test where we'll be measuring the deflection at different stages along our beam so that we can generate our deflection curve. Okay, we'll be applying the load in the middle of our beam. So for this test, we have the length of our beam set to 500 millimeters or 0.5 meters. Okay, and we'll be applying the load in the middle of our beam. Okay, so there are a few things that we need to do before we can actually start testing. As you can see on here, this number jumps around every time we start. What we do want to do before we start is that we want to zero this deflection here, so that we're obviously starting off with 0 deflection before we apply our load. Okay, now what we're going to be doing is essentially measuring the deflection, so we'll need to be moving this dial gauge. We want to measure the deflection at 25 millimeter increments, so every 2.5 centimeters. And you should see in your table there and in the results that we've provided that we have all that data there for essentially should be 20 different values across our beam. Okay, so we would start with putting the dial gauge at this first position here. Okay, we would zero that deflection that's on our dial gauge there. Sometimes it's a little bit tricky to get it to 0. If it doesn't zero, then essentially whatever the value is that you have at the start, you can then sort of tear that yourself by taking that value off of the final value that you do have. Okay, so just be aware that that is a valid way of doing it. Okay, so we'll be applying a 500 gram load for this test, and we'll be applying that in the middle of our beam. So again, making sure that that's directly in the middle. So in this case, we have a length of 500 millimeters, so we want to be applying our load at the 250 millimeter mark. Okay, so we would apply it there, and then read the deflection off of our dial gauge here. Now obviously we're finding the deflection at the support, which should be 0, and we found that it is 0 in this case. Okay, so then we would take off the load, then move the dial gauge to the next position. Okay, so moving a further 2.5 centimeters along. Okay, make sure that it's tightened at the back. Okay, make sure that this is positioned in the middle. We would zero that deflection on there and then apply our load here. Okay, we would wait for that value to settle, and then we would read that value off of our dial gauge there. Okay, so we would continue to do that, moving along another 2.5 centimeters. So this time we're at 50 centimeters, 50 millimeters along. We would then make sure that we're zeroing that deflection before we start, and then applying the load in the middle there. Okay, so just make sure it's applied directly in the middle, and then again read the deflection off of there. Okay, and we would do that so on and so forth until we've looked at the entirety of our beam. But it's important to make sure that we are, once we move this, that we are then zeroing the deflection, because although we may have the value up here to be 0, when we then move it to the next configuration, it might not be 0. Okay, because there might be some sort of a little bow in the beam, which there is in this case, and therefore that deflection value is not reading 0. So we would make sure that we would zero that before we then apply our load again. Okay, and then essentially we would just be doing that across the length of our beam. And what you should be able to do with that is then generate your beam deflection curve, and you'll also want to be using the theoretical equation to also generate that curve and essentially compare the two in your report. Okay, so that's the first test. So the second test that we'll be doing is again a 3-point bending test, but this time we're interested in the maximum deflection overall. So we will be applying different varying loads, and we'll also be using different lengths of our beam each time. Okay, so what we'll be doing is that we want to be calculating the deflection, the maximum deflection, which we should know for a simply supported beam with a load applied in the middle, occurs in the middle of the beam. Okay, so we'll be doing this for 3 different lengths with 5 different loads. Okay, so 100, 200, 300, 400, and 500 grams. Okay, so the first length that I'm going to do, I will move these here, and I will set my length to be 300 millimeters. Okay, so 0.3 meters. And because we know that the maximum deflection occurs in the middle of our beam, we then want to move our dial gauge so that we're at the middle of that beam, which is 150 millimeters along. So tighten it on the back. Okay, it doesn't matter that we have this extra length out here, because essentially these are acting as our 2 supports. Okay, so we want to move this to the middle because we're applying our load in the middle. Okay, we again want to zero that, zero our deflection, and then we will apply our 100 gram load and read the value off. And then we will take that load off, ensure that it is still has a 0 deflection, and then we would apply our next load, our 200 gram load, read the value off, then take that off, apply our 300 gram load. Okay, making sure that we've got this positioned nicely within the middle, read that value off. Okay, 400 gram load, read the value off. Sometimes if it's swinging, you'll see that the value moves around. Okay, so just make sure that it's nice and still, and then read the value off of the dial gauge. Okay, and then load it with the 500 gram load. Okay, and read the value off, and we'll give you all of these values. Okay, so then the next thing that we want to do is essentially change the length, so that we're then looking at a 400 millimeter long beam. Okay, and then we're essentially applying the same loads, making sure that we're applying that in the middle. So we will need to change where this dial gauge is positioned. We now want it to be 200 millimeters along, so halfway along our 400 millimeter beam. Okay, again, zero your deflection before you start, and then we'll go through, apply the 100 gram load, read the value off, apply the 200 gram load, read the value off, and so on and so forth until we get to our 500 gram load. Okay, so that's looking at our 300 millimeter beam and our 400 millimeter beam. We also need to do the same with a 500 millimeter beam. So again, move that to the length of 500 millimeters. Move this to halfway along, which is 250 millimeters. Okay, make sure that you're moving this to directly under it. If you're putting it over here, then you're not actually loading it in the middle of your beam. Okay, so applying that one there, we would then make sure that we zero it before we start. So it can be quite easy to forget to do that, so make sure that you are. And then apply that load there, read the value off, and so on and so forth until you get to your 500 gram load, and we'll give you all of that data. Okay, so that's the 3-point bend test when we're interested in the maximum deflection for varying lengths and varying loads. All right, so the third and final test that we'll be conducting today is a 4-point bending test. Okay, so the way that a 4-point bending test works is, again, we have our simply supported setup, but instead of just having one load applied in the middle of our beam, we have two equal loads, being applied 1/4 of the way along and 3/4 of the way along our beam. Okay, in this configuration, we still have our maximum deflection in the middle of our beam. Okay, we're interested in calculating the maximum deflections for, again, varying lengths and varying loads. Okay, so in your workbook, you will see that, again, we're doing this test for loads from 100 grams all the way to 500 grams, increasing at 100 gram increments. Now, in this case, when we're applying that load, we need to distribute that load over the two hooks that we have here. So here I have two 50 gram loads to get my entire 100 gram load, and I will apply each of those at their points 1/4 and 3/4 of the way along our beam. Okay, so in this case here, I've got my beam with a length of 300 millimeters, okay, which means my maximum deflection is in the middle, 150 mils along, and I'm applying my load from this end. It'll be 75 millimeters of the way along, which is 1/4 of 300, and then I'll also be applying the same load, 225 millimeters along my beam, which is 3/4 of the way along. Okay, so same principles here as the last one. We're just wanting to calculate our maximum deflection, which occurs in the middle of our beam. Okay, so setting this so that it's in the middle of our beam. Okay, making sure that we've positioned these at the correct distances along before we zero it. Okay, so then we want to zero that deflection there and then apply our loads. So to get my 100 gram load, which I'm applying, I want to apply my two 50 gram loads at their distances. So again, make sure that they're not shaking, make sure that they're applied at the right point, okay, and then read the value off of the dial gauge. Okay, we would then remove those, make sure that we line these up with the position that we want to apply that load. Okay, make sure that our deflection is still 0, and then now here I have two 100 gram loads, which will give me my 200 gram overall load, and I'm applying that 200 grams across these two loads, which means each of them will have a load of 100 grams. So making sure that I'm applying them directly where it says, and then again reading the values off here. Okay, and we would go and do that for the rest. Okay, so here I've got two 150 gram loads, which is going to give my 300 grams. Okay, so again, making sure they're applied in the right direction, right position, and then reading the value off of there. Okay, take these ones off, and then I've got two 200 gram loads, which is going to give me my 400 grams overall. Again, applying them at the points of interest, reading the value off of there, take that one off. And then finally, I've got two 250 gram loads, which I will be applying here at 1/4 and 3/4 of the way along my beam to get my total load of 500 grams. Okay, and then again, reading the value off of here. Okay, and then, so that was for a distance of 300 millimeters. So then I would change that to 400 millimeters. Okay, make sure that I now know that I need to change this because, as you can see, it's no longer in the middle of my beam. Okay, so the middle of 400 is 200. Okay, and then I'm applying these loads at 100 and 300 of the length along my beam here. Okay, so then going through, applying the same loads, making sure that they're applied directly at these distances here, making sure that you're zeroing it before you start. Okay, and then gathering the data for all of those different types of loads. Okay, we would then move to 500 millimeters along. Okay, so 250 is the middle of that, and then 125 here, and 375 here for 1/4 and 3/4 of the way along. Okay, again, making sure you zero it before you start, and then applying each of these loads so that we get the total load in the system. Okay, so that's the final test, and from that you should be able to see and compare your 3-point and 4-point bending to see which one generates more of a maximum deflection. Okay. In terms of the report, you want to be collating all of the data, generating some graphs. So you can, well, I would recommend using MATLAB or Excel to complete those, but as long as you do have a nice, neat, hand-drawn graph, preferably on graph paper, then that's fine to submit as well. Okay, so you want to be generating the graphs as shown in the booklet. And if you do have any questions, feel free to email us or jump into any of the tutorial Zoom sessions that we'll be running in the coming weeks. So the test that we've completed today, there are some sources of error. In particular, the weights that we've been using today are not exactly the values that we say that they are. Okay, so taking a quick measurement of this 500 gram weight, we can see that it's slightly less, so 497 grams, and that will be a source of error in your calculations. Okay, so you'll need to take that into consideration.